That Professor Andrea Liu from Penn here. Andrea got a degree at Cornell with Michael Fisher. She was one of the amazing postdocs that came through Exxon when Dave Pine and I were there. She then went to UCLA in chemistry, and since then she's been at UPenn in physics. She's done work in all sorts of things, in polymers and biology, and lots of things like that. But she's probably both best known for sort of organizing the field of jammed matter by writing an article with Sid Nagel, which was called something like, what was it?
Jamming is not just
jamming
cool.
is not just cool anymore.
Cool anymore.
In which they presented a phase diagram which sort of organizes everybody's thoughts about jamming.
Wasn't there a sequel?
What's that?
Jamming is cooler than you use, even cooler than you thought?
No.
Not written by me.
So she's going to tell us about jamming and mechanical tunability.
Okay, thanks. Well, I've been having great fun here as always. It's always so fun to come up here and talk to people. And don't forget to remind me, Paul, that I have this thing to hand around.
Okay, you can give it to me a second.
Already? No. People don't know what to do with it yet. Not yet. Okay, well, you can play with it until it's time.
Great.
You need an overhead projector for that.
I got movies, but yeah, this is my wallet version. I just have it carried around my wallet. Okay. All right. So, yeah, I'm going to tell you about some work today. The beginnings of it are quite old now, but it's gone off in a bunch of new directions that we're pretty excited about right now. Most of this is work that has been done with my terrific collaborator, Sid Nagel at the University of Chicago, and some of the more recent stuff was done with Jim Sutton at Cornell, and we've had a bunch of terrific students and postdocs, and I particularly want to highlight Jason Rocks, my current graduate student, and Carl Goodrich. I should really say Harvard because he's now a postdoc there now, and he's two absolutely terrific graduate students. Okay. You can also say that this story about jamming is a tale of two rigidities, because it's the story of the jam state in contrast to the perfect crystal. Okay, so right now I'm teaching condensed matter physics. Not right now. I should have been teaching that today. It's basic. Most of it is the story of the perfect crystal, right? And we tell this story, the perfect crystal, every semester, every university, right? Because even though it's something that never occurs in practice, right? It even in principle could only be something that you could see at zero temperature. It's really a Platonic ideal. It's really the extreme limit of order, where everything is perfectly ordered. And why is that so useful? Why do we teach it all the time? It's really because it's not only a useful limit. It's not only an extreme limit, and it's always useful to study extreme limits, but it's a very robust limit, so that even if a crystal is not perfect, many of these features survive, and that's what we talk about. Okay, our question for a long time has been, what is the opposite? Is there a polar opposite to the perfect crystal? Okay, and one of the things I'll be arguing today is the polar opposite of the crystal is the jam solid, which you guys know a lot about because of your former colleague Mathieu Viard. So I'll be talking about why the jam solid is really an anticrystal. Okay, so now why is this a useful question? So the reason why is because if you think about something like a glass, okay, which is disordered, you can't get there just by adding defects a little at a time to the crystal. The properties of the glass are really fundamentally different from those of the crystal. In fact, the properties of glasses are in many senses universal, in that if you look at the low temperature properties of glasses, for example, the behavior of the specific heat or the thermal conductivity, you see the same thing in all different glasses, and the reason for this is not understood. Okay, so we can't get there just by perturbing the crystal. The behavior is totally different from what you get with the crystal. So so that's one reason. If we want to understand the glass, we really need a new way of thinking. Okay, and another reason why we need a new way of thinking is to study the glass transition, because if we're going to understand the glass transition, it takes a lot of chutzpah to study a transition when you don't even know one of the states that you're making a transition to. Okay, and so, and where you start with understanding glass, you start at understanding it at zero temperature. Okay, so so that's really, you know, our motivation in the end for studying this. The other thing is that, you know, the glass, right? The key about the glass is that it has a very rough energy landscape. So there's an extensive entropy. It's a system which has an extensive entropy of energy minima in the landscape, right? So that means that for a system with only 1,000 particles, you have, you know, 10 to the 200 already minima. Okay, that's a lot of minima to deal with. And this is the starting point for understanding how to deal with them. Okay, so the key to jamming is to restrict yourself to a certain class of potentials. And these are potentials in which the particles don't interact if they don't overlap. We're only going to consider spheres, okay? And if they overlap, they repel. And as they overlap more, they repel more. Okay? So this power alpha, if it is greater than or equal to 2, if it's equal to 2, it's just harmonic springs, harmonic repulsive springs, so one-sided springs. Okay? All right, so what are we going to do? We're going to study the minima of a system of spheres interacting with this potential. So if you start with some random initial configuration, it doesn't really matter too much what you start with, okay? And then you quench down to the nearest local energy minimum, okay? There's sort of one or two possible outcomes. Either you can be a low density where none of the particles are overlapping, okay? And they're all just sitting there, they're all happy. And the energy is zero. It doesn't cost any pressure to keep them like this. Or you can quench them at a high enough density so that there's a network of repulsive forces between them pushing them apart. And that's what's drawn here is this network. Okay, and then it takes a certain pressure to hold them together, and the energy is now greater than zero. Okay?
Two radii here.
Yes. Yes.
And they're not up there.
That's right. So often in 3 dimensions, we just study the monodisperse system. In 2 dimensions, because there's such a strong tendency to crystallize, we tend to study bidisperse systems. But it turns out that all the results I'm telling you about are robust to polydispersity. As long as you can't fit small particles in the interstices of big particles, you know, as in an Apollonian packing, that sort of thing, then things get a little bit different. Okay, but until you reach that limit, it's very robust. It's completely robust. Okay. Oh, these results.
Also the same bidisperse.
Yeah, so this is a bidisperse system, and this is too. Yeah. Okay. Is that the subway or something?
Yeah. Right in the wall.
It goes right through here. Okay. All right. Okay, my initial thing was, because I was at UCLA for a while, earthquake. And then I realized it's going this way. All right, so as I said, there are an extensive entropy of energy minima in a system like this, and that's actually been measured now by Don Frankel and explicitly shown. And we now know from exact solutions in infinite dimensions that at least in infinite dimensions, the energy landscape is actually fractal. So there's actually a parallel distribution of energy barriers and energy minima. Okay. And so if you have so many minima, and we're studying the properties of individual minima, right, then we have to think about what is the nature of these minima. And, you know, the point is that if every minimum were completely different, you know, we wouldn't be here talking, there would be nothing to talk about, because every time an experimentalist prepared a low temperature glass, okay, you'd end up in a different minimum, or she. Okay, you'd end up in a different minimum and you get a totally different result, right? But you don't. These results are reproducible. They're seen in experiment after experiment. They're reproducible. And that tells you that these minima have a lot in common. Okay, even though you're exploring different minima, And which minimum you end up in depends on your history. Somehow there's something very similar about them so that you can actually make sense of their behavior. Okay?
Well, am I supposed to understand precisely what that means?
A fractal energy landscape or what?
Well, the two different minima. Is that something
This picture
minimum
here?
are completely different from every other one, but what does that mean precisely?
If they had different properties, right? So if they had different properties,
If each quench
resulted in a minimum which had different properties, it's not a theoretical concept, it's a practical concept. I'm just saying, we see reproducible experimental results. And therefore, that tells us that different energy minima actually have similar properties. Okay, and really jamming is the study of the properties of these minima. It's really the study of the statistics of these minima. Okay, and the point is that they do indeed have similar properties, and averages of quantities such as the pressure, the bulk modulus, the shear modulus, etc., obey power law scaling that depends on the distance from the jamming transition, which I'm going to tell you next. Okay? All right. So the jamming transition is the transition from this state to this state. So if I have a configuration that's just below, at a density just below it, I have no interactions. None of the particles are overlapping. If I'm right at it, I have a bunch of particles that are just touching. And if I go over the jamming transition to a higher density, now I have repulsive forces. Okay? A network of repulsive forces pushing them apart. And the interesting thing about this, the amazing thing about sphere packings is that if I'm just above this density, this critical density, there are actually a non-zero number of overlapping neighbors per particle, and the number of neighbors is exactly twice the dimensionality. Okay? And, I thought I changed this. Okay. This is really, really old results. We now know it really in the thermodynamic limit it is exactly twice the dimensionality. Okay, and there are corrections of order 1 over n, which we understand. All right, and if I go now above this point and I keep compressing, the number of overlapping neighbors increases as a power law above that constant value of twice the dimensionality. So where does twice the dimensionality come from? This is something you may have seen from Mathieu. It comes from just matching equations and unknowns, and the idea goes back to this guy. Who's this guy? Thank you. Yes. It's amazing how many places I go and people don't recognize him. Okay. So a lot of people think he's famous for electromagnetism. Okay. So he also studied a very healthy area of mechanics. Okay, and he was the first really one to ask, okay, so suppose I have a bunch of particles that are in contact, and I want to ask, is this whole thing mechanically stable? How can I tell? Okay, and he pointed out that if I have n spheres, for example, the case that we have n spheres, no friction in d dimensions, then what I need is enough constraints to constrain all my degrees of freedom. So I have n times d, if I'm in d dimensions, degrees of freedom. And how many constraints I have, those are given by the forces on the particles, right? The constraints are coming from the interactions with their neighbors. And so if I have z neighbors per particle, the total number of constraints is nz over 2, because each bond is shared between two particles. And so you see that if I need a number of constraints greater than or equal to the number of degrees of freedom to be mechanically stable, and that gives me this condition. And the beautiful thing about sphere packings is that we have exactly the minimum number that are needed at the onset of jamming, okay, at the onset of this overlap between particles. So it's the minimum number of contacts needed for mechanical stability. That doesn't mean that it's enough. Right? I mean, some of them could be wasted. I could have degeneracies. But indeed, it is actually enough. The onset of jamming is truly the onset of rigidity, and it's the onset of a shear modulus. So if you look at where the number of neighbors jumps to 2D and then starts increasing on its power law, if you look at where that value of the critical density is, that's exactly the same value as where the shear modulus will vanish. It's the same density of where the pressure will vanish. So the onset of overlap corresponds to the onset of a non-zero bulk modulus and a non-zero shear modulus. Okay? Now if I think about the scaling of the pressure, it goes like the amount of overlap, phi minus phi c, the critical density, raised to the alpha minus 1. And if I go back, you can't believe I still get this wrong. Okay, but the potential goes like the amount of overlap to the alpha, right? So the pressure is depends on the force, which is one derivative of the potential. Okay, so it goes like phi minus phi c to the alpha minus 1. Okay?
And this is true for any alpha bigger than 2?
And this is true for any alpha greater than 2. That's right. Okay. The shear so the bulk modulus, which is a derivative of the pressure, will go like phi minus phi c to the alpha minus 2. Okay? And the shear modulus, though, goes with a different power. It goes like phi minus phi c to the alpha minus 1.5. Okay? So the shear modulus scales differently from the bulk modulus. And that's interesting because what that says is, in fact, the ratio of the shear to bulk modulus is independent of the potential, and it vanishes at the critical point where the number of contacts in excess of the minimum number you need, in excess of 2 times the dimensionality, what we call delta z, goes to 0. So this is the excess contact number. And so at the jamming transition, the ratio of the shear to bulk modulus vanishes. Okay. And in fact, for the rest of this talk, what I'm going to do is I can define a effective spring constant, which is 2 derivatives of the energy. Okay, so that goes like phi minus phi c to the alpha minus 2 power, and I'm going to divide that out. Okay, I'm going to scale the pressure by that spring constant and the moduli by that spring constant. I'm going to just divide out that power, and so everything will look as if the same as if I have just harmonic repulsive springs. Okay, and that trivial rescaling just takes out all the potential dependence. Okay, once I rescale by that effective spring constant, then the potential dependence goes away. Okay, all right. All right, so now if I look then at the ratio of the shear to the bulk modulus, and let's look at a crystal made out of the same particles. Okay, let's think about a crystal made out of particles with the same potential. If I'm well above overlap, okay, I have some bulk modulus and some shear modulus, right? And the ratio of it is actually about 0.6 for the perfect FCC. That is the most stable phase. Okay. Now, if I decrease the pressure, then I'll get to a point where they're just touching. Okay, and then they will vanish. Okay, and so the ratio of the bulk, this is non-zero. Okay, but then both the shear and the bulk modulus. So if I think about the shear modulus of the crystal, it's 0 below the onset of overlap, and once I have overlap, it just jumps to this non-zero value discontinuously. Whereas the jam state, okay, does something very different, right? The shear modulus goes to 0 continuously as I decrease the amount of overlap, okay, until just at overlap it goes to 0. Okay, so the onset of rigidity is discontinuous for the crystal, and it's continuous for jamming. And remember a liquid has a bulk modulus but no shear modulus, right? So the jam state, just at the jamming transition, the jam state is behaving like a liquid. Okay. All right. So then comes an idea which is really something originally posed by Mathieu Viart, which is that if I think about this system, it's not at the onset of rigidity, okay, I have just barely the number of neighbors that I need for mechanical stability. That means if I take one bond away, it's going to be unstable. Okay, so it's right at the edge of, the system is certainly marginally stable. Now, if I compress the system, okay, I'm going to get rearrangements, and I'm going to get more contacts. The number of contacts, remember, increases as a power law. Okay, so I'm going to develop more contacts. I develop just enough contacts to support that pressure. Okay, so that if I squeeze a little more, it's going to go unstable again and develop more contacts. Okay, and so in order to support that higher pressure. So it's not only marginally stable at 0 pressure, but it's marginally unstable at every pressure, which says that you can't make a solid, okay, that's in this regime over here. If you're going to make a solid, it has to be lying somewhere between the crystal limit, okay, of the FCC and the jam solid. You can only make states that are in here. Anything in here is not going to be rigid. You can't have a shear modulus if you're in that regime, because it's not going to be stable. Okay? So because this state is marginally stable, okay, this really is the opposite limit that you can have at any pressure to the crystal. At any pressure, the crystal is the most stable state, okay, and the jam state is the least stable. Okay? And therefore, that's why we call it the anticrystal. Okay? It's because it is really the opposite pole to the perfect crystal in terms of rigidity or instability. Okay? It's got the lowest shear modulus that you could possibly have, and it is the least stable. Okay? And it's not the anticrystal in terms of structure. People have always thought of it as what is the most disordered structure you can make? But what does disorder mean? Okay? We don't know what disorder means because it's only the opposite of order, right? And who knows what kind of order that we can have. In fact, the jam state has a very special kind of order to it called hyperuniformity. So there is some special order to it, okay? But so it's not necessarily the opposite in terms of structure, but it is the opposite in terms of stability. All right, what does that do for us? Well, it turns out it's really interesting. If you look at what I've showed you so far, I said the number of contacts jumps and then increases as a power law. The pressure scales as a power law. The shear modulus scales as a power law. The bulk modulus is discontinuous, but that's a power law of 0. I didn't show you, but there are actually 2 diverging length scales that result from marginal stability as well. Okay, and so not only is the jam solid the anticrystal, the opposite to the crystal, but at its extreme limit of 0 pressure, or just right at the jamming transition, it has these things that sort of make it look like a critical point. Okay, but it's a weird critical point. It's not your normal thing. It's got this discontinuity. Okay, and in fact, really, we've been thinking, if you look at these exponents, it turns out that they agree with what you get for the mean field glass transition. That you get actually the same kinds of exponents, which is a random first order phase transition. So it's not your usual critical point, and in fact, it's got 2 diverging length scales associated with it, not just 1. Okay, so it's sort of a weird beast. Another interesting thing about it is that the exponents are the same in 2 and 3 dimensions. And they've now been looked at dimensions up to 10 numerically, and at least within numerical precision, they are the same. Okay? And now, in fact, based on the finite size scaling, we believe that the upper critical dimension of the system is 2, so that the exponents are mean field-like in dimensions greater than or equal to 2, and that's why they're the same, okay, in all dimensions that we have. Okay, so it's an unusual phase transition. So now what I'm going to show you next is that we really believe, though, even though it's this unusual phase transition, that we can think of it in many ways as a normal critical phenomenon. Okay, and that's because we've developed the scaling theory for it. So I just want to first just remind you of criticality in the Ising model, right? So in the Ising model, right, you have spins that can point up or down. You have a nearest neighbor interaction that wants spins to line up together. And at low temperatures, there are 2 possible phases: a possible phase with positive magnetization and that coexists with one of negative magnetization. And above some critical temperature, there's only 1 possible phase. Okay. And if you look at the free energy of this system, okay, in terms of this is called the reduced temperature, the distance away from the critical point. It was shown in 1965 by Ben Whittam that you could write it in this scaling form, okay? So that the free energy, which is a function of the temperature and the magnetic field, and if I have a finite system, the system size, okay, that you could write it as a function of only 2 of these variables, okay? A function of only 2 variables. Written in the scaling combination where I take h and I divide it by t to some power, and I take L and I multiply by t to some power. Okay. The nice thing about this is it ties together everything, so that if I look at the derivative of the free energy with respect to the field, which is magnetization, I get a power here, and it has the same form. And this power is just 2 minus alpha minus delta. Okay, just from taking the derivative of this thing with respect to h. And if I take 2 derivatives, I get a susceptibility which diverges with an exponent gamma, where minus gamma is 2 minus alpha minus 2 delta. Okay, and it's again written in the scaling form. Okay. The nice thing, so this, this was the first step right towards our eventual understanding of criticality of the Ising model. Then Leo Cadnock came along and said, aha, I can do coarse graining rescaling, and I can get these scaling relations, and then Ken Wilson, Michael Fisher, and so forth showed that we could we can construct a renormalization group and really solve this. Okay, so so that's what we've got, and now what I want to just tell you a little bit more about the Ising model is what happens if we're in the situation that we're in, where we're at or above the upper critical dimension. Okay, it turns out that what you do is you replace this thing, which depends on the system length, okay, with something that depends on the number of spins in the system, or L to the D, okay, and then that scales as t to the upper critical dimension times the mean field exponent. Okay, so instead of scaling with system length, this now starts scaling with total system size. That's the difference. Okay, all right. So now it turns out that we can describe the jamming transition with the scaling Ansatz. So we can do for the jamming transition what Whittam did for the Ising model. Okay, and so we can write down an expression. And now what's the right free energy? Well, we're at 0 temperature, so it's just the energy, okay? And it's the elastic energy of the system. That's our appropriate free energy. So I can write this elastic energy as some power. And now what plays the role of the reduced temperature? We're going to take actually the excess number of contacts. So this measures how far we are from our critical point, okay? What are the scaling variables that enter in? Well, here instead of L, as I told you, I have the total number of particles in the system, okay? And now what do I have here? Instead of just the magnetic field, I have two different fields, okay? One describes the response to compressive strain. One is for compressive strain that I could apply, and the other one is shear strain, okay? So this was the key. And this is what allows us in the end to have different exponents for the shear and bulk modulus. So it's key to treat these two separately. Okay, if you write a scaling Ansatz in this form, okay, then just as I took
Can you repeat that last bit of what
yeah, I have compressive strain here, which is my distance from the jamming relative to the jamming transition, divided by excess contacts here, and then I have shear strain. So I have two different strains, and I really have to treat them separately. And maybe in the end, we'll have to have all the tensorial invariants of the strain tensor. Okay, right now we just have the simplest possible formulation that we need for this. Okay, so for each strain invariant, we would introduce that as another field, like the magnetic field in the Ising model. Okay, all right. If you do this, right, just as the magnetization is one derivative of the free energy and is the order parameter for the Ising model, if we take one derivative of the elastic energy with respect to the compressive strain, we get the pressure. If we take two derivatives, we get the shear stress. And so the pressure and the shear stress emerge as order parameters in this description. Okay. Alternatively, though, I could put the pressure and the shear stress here, and then the strains would emerge as order parameters. You could think of it either way. It's just a Legendre transform. Of this. So, all right, so the pressure and shear stress are order parameters, and then I get the bulk modulus, okay, and the shear modulus are second derivatives. So they're like susceptibilities or inverse susceptibilities, okay? Okay, so these, they come from this. And in fact, if I do that, okay, if I look at this, I have actually 8 exponents. These 5 here and these 3 here. I have 8 exponents. Right from here, from these equations, I have 4 scaling relations, because delta P must be zeta minus beta phi, for example. So I have 4 scaling relations coming from this. We have a 5th scaling relation I'm not going to tell you about, okay, today, all right. So this says then, if I just specify 3 of the exponents, which I can do either based on arguments from theoretical arguments based on marginal stability, or we could take them from the simulation results. So I'm going to just choose 3. That means then I can fill in the other 5. Okay? The scaling theory allows me to fill in the other 5. And the other 5 are, of these, 3 of them were measured before, and the values we get from the scaling theory agree with what we knew they should be from simulations. and some theoretical arguments. Okay, and that leaves 2 that are new. Okay, this one is still in the process of being checked. There are 2 papers out now, or on the archive now, and then there's this exponent which we checked, and that implies a certain scaling for the shear stress, and we verified that scaling is correct. Okay, so this scaling theory really works. Okay, it ties together everything we know about jamming, and it really says that the exponents that you get for the energy, the pressure, the shear stress, the compressive strain, the shear strain, the bulk modulus, the shear modulus are all related together. Okay, they're all connected. Okay, so we're happy. Okay, so not only is the rigidity onset continuous for the anticrystal, but it's actually critical. Okay, and criticality, right? The nice thing about criticality is that once we have this scale invariant form for our free energy, which is the elastic energy, we now know that we can do RG. Okay, there must be some way to do. We know that this implies that an RG renormalization group should exist. We should be able to coarse grain and rescale, okay, and be able to understand this. Why is this important? Because I've been talking to you now for a while about frictionless spheres interacting through these special potentials. These are not things that exist in reality. We're trying to understand glasses, okay? And so there are all kinds of things, all kinds of effects that glasses have that these don't. Long-range interactions, non-spherical shapes of molecules. You know, all these things become important. And what this says is that if we can construct the RG for it, okay, people think of RG as being useful for exponents, calculating exponents if you're below the upper critical dimension. Okay, but that's only part of what it's really a tool for understanding universality, right? It's a tool for understanding, okay, if I coarse grain like this, all these effects go away, and in the end, I just see the same thing that I would have seen for the simpler model. And so the idea is if we can understand how to do the renormalization group for this thing, maybe we could understand, okay, what are the RG flows like for a system with long-range interactions? What if I add friction? How does that affect things? Okay, and so we can really answer this question of how many of the common properties that are seen in glasses come from universality associated with the jamming transition, okay, which has been our goal for quite a while. So we're excited about this. The other thing this says is that because glasses, unlike crystals, okay, where the rigidity onset is first order, it's a first order transition. We never understand that much about first order transitions, right? But we can understand a lot about critical phase transitions, so maybe someday we'll understand glasses even better than we understand crystals, which would be really nice, okay? But, you know, why do we, as I said, we spend a whole semester teaching about the perfect crystal because it's robust, okay? I can add a little bit of disorder and I still get the same result. Okay, so what about the anticrystal? Is it as robust as the crystal? Okay, and so we created states with tunable amounts of order. And the way we did that was to start out with the perfect crystal. We start out with the FCC, but I'm just illustrating with 2 dimensions. And then you can just take a particle at random and stuff it in somewhere at random, and then minimize the energy. Okay, or I could take out 2 particles, okay, and stuff them in at random, minimize the energy, and so forth. And so by doing that, if I take out all of the particles and stuff them in at random and minimize the energy, I will end up with a jam packing. That's in fact one way that we make jam packings. Okay, so this is a way to tune from one limit to the other. And what do you get? So here are systems with different amounts of order. Here's something that's very close to the perfect crystal. Okay, if I look at the shear ratio of the shear to bulk modulus, it looks like that of the perfect crystal. S6 is the amount of local order, the average amount of order in the system. It's a quantity that characterizes order. Okay, so if it's 1, it's perfectly ordered. Okay, if it's 0, it's not very ordered at all. Okay, it's not.
It's related to how many of these particles you have.
It's related. Yeah, it's related to the bond orientational order, actually. But it's basically, if I look at the neighbors of this particle and their orientations, and I look at the neighbors of this particle, how similar are their orientations? Okay.
So it's a response to having taken out and replaced randomly some finite fraction. But it isn't that. It's a response to it in terms of correlation.
This is a structural, this is just characterizes the structure. That's right. Okay, it's just telling me how correlated is this structure. And it's 1 for the perfect FCC. Okay. All right, so here is my perfect FCC. Here's my jam system. Okay, it's got a very low value of F6. Okay. Now, I'm going to look at this system. You'd say, hey, this looks pretty ordered. Right? This looks pretty ordered to me. Okay. So here's the behavior of this system. The ratio of the shear to bulk modulus is a function of pressure. It's straight, it's flat, as I showed you. The jam system goes to 0 as the pressure goes to 0 as a power law of 1/2, as I showed you before. What about this system? It looks like that. That's the purple line. Okay? So this system, which you would say is very ordered, behaves mechanically exactly like that one. Okay? And in fact, we can do this for thousands of packing. It turns out a little bit of disorder is enough to make it look jammed in terms of its mechanical response. Okay? So we've done it now for thousands of packings, and if you add, the more order you add, you get something that it shifts the prefactor, but the scaling basically remains that of the jam system until you get to extremely high amounts of order, very close to 1. Okay? So it's not only an opposite limit to the crystal, but like the crystal, which is robust to a little bit of disorder, it's robust to a little bit of order. In fact, it's even more robust than the crystal is. Okay, so it's robust to very high amounts of order. Okay, so all right, so that's jamming. So now I want to say, all right, the nice thing, right, about studying disordered minima is that, you know, by changing the contact number, okay, by changing the distance of the jamming transition, I could tune the ratio of the shear to bulk modulus to be anywhere from 0 to something quite large, like the crystal. Okay, so by accessing these disordered structures, I can really tune the value of my shear to bulk modulus in a way that I can't do for the crystal. Okay, can we do even better, get even greater tunability by choosing other ensembles of the disordered states than the ones that we look at for jamming? Okay. So now I'm going to switch gears a little bit and talk about disordered networks. Now these networks are related to jamming networks. Okay, so let me show you how we make these. Okay, look at the properties. So if you take a jam packing, okay, and turn it into a network by replacing the center of every particle with a node of my network, and then in between every pair of overlapping particles, interacting particles, I'm going to put a spring. And I'm going to put a spring that's happy. It's at its equilibrium length. Okay? Then I end up with a spring network like this. The interesting thing about the spring network is that if I look at the scaling of the bulk modulus with respect to the number of now, instead of contact number, the equivalent of contact number is the number of springs that are attached to each node. Okay? That's what Z is the number of springs that come out of each node. Okay? So if I look at the bulk modulus as a function of that contact number, it looks exactly like what happens for the jam packing. It has the same scaling, and the shear modulus goes to 0 just as it does for the jam packing. So these networks that are derived from jam packings, in fact, show the same behavior of the ratio of the shear to bulk modulus as jamming. Okay?
Are these identical springs?
Yes, they're identical stiffnesses, different lengths, because each of them is at its equilibrium length. I'm just going to put it in so that each one is happy at its equilibrium length. Okay? All right. If I start out with a network like this, okay, and now instead of getting networks with lower values of this coordination number by starting with jam packings that were less compressed, if I instead just start cutting bonds randomly to get a network with the same coordination as this one, and I keep cutting until what happens is that as I keep cutting, the bulk modulus goes to 0 and the shear modulus goes to 0. So I get a different scaling. Okay, so if I cut them randomly, I get a different result than if I make these networks from the jam packings, because in the jam packings, I'm not cutting these bonds randomly. Okay, they're cut in a special way. Okay, so that it's jammed, it's marginally stable at each point. If I just cut them randomly, I get a different scaling. The ratio of the shear to bulk modulus is constant. They both go to 0 together. And that's actually what you get for a different transition. This belongs in the universality class of a different transition, which is rigidity percolation. Okay. All right. So why am I telling you this? Okay, because now we can, what do we call this, tuning by pruning? Yeah.
Isn't it just thinking about the differences with some of the forces on every particle being 0, so you always have positive forces in one case versus in the other one you can have compression and extension? So
Yeah,
spring,
that's why they're the same. I'm just replacing a one-sided spring by a two-sided spring.
Okay.
That's really what it is. Okay. To go from jamming to this network. Okay. All right. So now let me take this system. I told you that if I prune bonds randomly, okay, the shear modulus will go to 0, like delta z. Okay, as I prune the bonds. Now let me, instead of pruning bonds randomly, I'm going to prune the bonds that make the smallest contribution to the bulk modulus. I'm going to look at how each one contributes to the bulk modulus. I'm going to take away the one that makes the smallest contribution. What happens to the shear modulus? It still scales like delta z. In fact, here, if I remove them randomly, I get the crosses. If I remove the ones with the smallest contribution to the bulk modulus, I get the blue squares for the shear modulus. This is the value of the shear modulus as I keep pruning. If I prune bonds that make the largest contribution to the shear modulus, what do I get? Oh, sorry. The largest contribution to the bulk modulus, sorry, I'm on this one, I get the same scaling for the shear modulus. It's right on top. In other words, no matter which bonds I pick for how much they contribute to the bulk modulus, the way they contribute to the shear modulus remains exactly the same. It's as if I chose them entirely randomly. Similarly, if I prune the bonds that make the largest contribution to the shear modulus, the bulk modulus scales as if I took them away randomly. So what this means, okay, is something very interesting. We call this the principle of bond level independence, which is that how much each bond contributes to the bulk modulus is completely uncorrelated with how much it contributes to the shear modulus. Okay? So once you have that, and it's not just bulk and shear. We could do this for different elastic constants or different things. Okay? So now, what can we do with this? That means now, let me now take away the bonds that contribute the least to the bulk modulus. Each time I'm going to contribute the ones that contribute the least. Well, then the shear modulus is going to decrease as if I'm pruning randomly, but the bulk modulus is not going to change at all because I'm always taking away the ones that contribute the least, and that contribution is very close to 0. These distributions are continuous, and so the bulk modulus essentially doesn't change, and I get the scaling that we see for jamming. And that's what jamming is doing. It's always removing the smallest overlap. As I decompress the system approaching jamming from above, I'm removing the smallest overlap. Okay? Now, though, suppose I prune the bonds that make the largest contribution to the bulk modulus. Okay? Then the bulk modulus is going to drop like a rock. Okay? While the shear modulus behaves as if I'm pruning randomly, and then the ratio of the shear modulus to the bulk modulus is going to go shooting up, and it shoots up with an incredibly high power, close to 10. Okay? If I remove bonds that make the largest contribution to shear modulus, similarly, the ratio is going to go down really rapidly. Okay? So that by removing only about 1% of the bonds, I can change the ratio of the shear to the bulk modulus by 20 orders of magnitude in this plot. Okay? Just by removing the right bonds. Okay? So this is what we call pruning by tuning, or sometimes we call it making by breaking. Okay? So by breaking bonds, we can make these things. So we get the same results in 2D. Okay? So why is this cool? Okay? It turns out that materials with the ratio of the shear to bulk modulus, which is greater than 2 over the dimensionality in d dimensions, are what are called exotic. And I just copied this video from YouTube to show you what an exotic material is. Right? Most materials, if you took this thing and now you pulled it apart, you would expect it to get thinner, right? You pulled something apart, it should get thinner. These get fatter. Okay? So that's called an auxetic material. It's a negative Poisson ratio material. Okay, so that if you stretch in this direction, it actually gets fatter in this direction instead of shrinking. And those are good. People are interested in those because if you bang on it instead of getting less dense, it'll actually get more dense. So it's good. So actually, NIST has given a huge grant to Juan de Pablo at the University of Chicago to make better football helmets. Okay. For concussions and the NFL, and one of the ideas that we're pursuing is this. Okay, so for making auxetic materials, because we have no trouble in making the ratio of G over B greater than 2 over D, we can make it, as large as you want, right? I showed you we went up to 10 to the 12th, easily. This is actually a new principle for making auxetic materials. So this was a recent review that came out saying, okay, so this is the ratio of B over G in this case. Okay, so in this case, this is maximally auxetic. This is called the incompressible limit, where G over B goes to 0. That's what we get at the jamming transition. Okay. And they say, okay, the way to get these different materials, either you make a denser packing or you change the connectivity. If you increase connectivity, you can go from this limit to this limit. Okay, what do I have? We've got 2 networks, right, which are at exactly the same density and the same connectivity, and yet they can have totally different ratios, so G over B. Okay, so we're not. This is a totally different way of making auxetic materials. The other thing is sort of experimentally natural, because imagine I have a network. If I were Ludwig Leibler, I would know how to do this. I would make a polymer network where once a bond got above some threshold stress, it would break. And now I would compress this thing or pull on this thing. Okay. If I do that, then the ones that are under the greatest stress will break. Those are the ones that make the largest contribution to the bulk modulus. So this system will naturally tune itself to the auxetic limit. Okay, so I think it's actually something that is reasonable to.
Because once they break, they're out of commission.
Because once they break, they're out of commission. So I've pruned them. Okay. Yeah.
But actually, you may have those brokers in multiple networks. No?
What?
In multiple networks that share the networks. They will have that.
They have actually. I know they have actually make things that have that property. Yeah. But they haven't tuned them to actually the auxetic limit to notice that they were auxetic. Yeah. So it is definitely something that is possible to do. A clever enough chemist can figure out how to do it. Okay. So they have figured out how to do it. Okay. So now we can tune these global responses, the shear modulus, the bulk modulus. What about a local response? Okay. So this is something that is very important in proteins. So the proteins have this thing called allostery. So a protein, for example, take an enzyme. Suppose this thing comes in, it's a small molecule, okay, and it comes in, it binds to the protein, and it gets phosphorylated. Okay, that's what the protein does, it phosphorylates this thing. Okay. Turns out that the action of this protein can usually be regulated by some other small molecule that comes in and binds somewhere else. And once this binds somewhere else, okay, this thing can no longer bind. And the weird thing is that it's usually quite a different spot on the protein, as they have in this cartoon. It's really one small molecule binds over here. It changes the positions of the configuration of the protein by angstroms over here, and then it somehow turns off the enzymatic activity for this thing. It turns out the ability of another small molecule to bind way over here. Okay, how does that work? That's been a problem that there are thousands of papers devoted to this with not a whole lot of understanding. And one interesting thing I just want to point out, it turns out that there are many, many different signaling proteins that actually have the same folding structure, but have totally different functions. They signal for totally different ways. Okay, so different things come in to make them do different things. Okay, different things bind to them and cause them to respond in different ways. But they have the same basic folding structure. Okay, so this is a weird thing. So then we said, okay, can we use this idea then to understand some of the fundamental principles that might govern allostery? So we want to now generate a localized response to local perturbation. So again, we're going to take our networks. Okay, and now Paul, you can pass that thing around. Okay, So the idea is that thing that Paul's going to pass around, there are 2 red sites, okay? Those are output sites, okay? Okay, and then there are 2 blue sites, those are input sites. So pull the 2 blue sites apart very gently. I don't want you to break this thing. Okay, very gently. And then this thing has been tuned to have a large response at the output sites, which are covered red. Okay? So what we're going to do is we want to tune, the way we did it is we tuned the ratio of the output strain, the distance between these 2 output sites, compared to the input state strain. How much do we move these 2 apart? We want to tune that ratio to be large. So for a small pulling apart here, we get a big response over there. Okay?
By tune, you mean to choose the pole to this network as to maximize this response.
So I'm going to start with some generic network that, in fact, we made from a jam packing. Okay? And now I'm going to remove, what I want to do is remove the right bonds. I'm going to prune the right bonds to get a very large response over here. Okay? So again, I'm tuning by pruning.
This ratio.
I want to tune this ratio by pruning bonds. I want to figure out which bonds do I remove to do this. Okay? So, so what do? So we calculate the change of the strain ratio of the input to the output response due to the removal of each bond. And this can be done in a very efficient way. It's just a linear algebra problem using this formulation of states of self-stress, non-states of self-stress that was developed by Pellegrino and Calladine. Okay? Once you do that, you can remove the bond that gives you the largest change in the strain ratio, and then you just calculate it again and repeat. Okay? It turns out you only have to calculate it once. You can. Okay. Anyway, you can do this extremely efficiently using this sort of formalism. Okay. So here's our initial network. Okay. And if these are now my input sites. I'm pulling them apart, and you look at the output, nothing. Right? This is just what I started with. And I could have chosen any 2 sites here and any other 2 sites here. Okay?
Screen.
Yeah, it's screened. There's really nothing going on here. So now what I do, I'm going to take 2 cases. Okay? In one case, I want to get a contraction. In other words, I'm going to pull these 2 apart here, and I want these 2 to get closer together. In the other case, I'm going to tune so that when I pull these 2 apart, these 2 are also going to move apart. Okay? And I've pruned the bonds that you see dotted in red. Okay? And now you can see what I get. Okay? I've pruned these to get close together, and I've pruned those to get farther apart. Okay? So we were able to do it. So we're able to tune in that localized response that we wanted by removing those nodes. And if you look at the ones that are removed, there's actually a lot of similarity in the ones that are removed for these opposite responses. They're not totally the same.
Number.
It's about the same number. It's about 13 to 14 in the 2 cases.
But you don't constrain it to be the same.
We didn't constrain it to be the same number. Okay.
That isn't optimized.
What?
It's not optimized.
This is not optimized. No. So, all right. So now I can tune multiple outputs. So here's a case where I have one set of input sites, and I've tuned these and these and these all to respond to the. I've tuned these all to respond to the same thing. Okay, and I've tuned them in different ways. Yeah. Okay.
The input is which, the yellow?
The input is the yellow, and the output's 3 sets of green sites.
And their responses are identical?
I wanted them, in this case, yes, I wanted them all to get closer together. But I could have chosen some to get closer together and others to be further apart. Okay, yeah.
Is the idea that the Poisson shear modulus of this object doesn't change very much?
That's right. They haven't changed very much. As far as the Boltzmann shear modulus are concerned, they've been removed randomly.
Sorry, what are the dashed red ones?
These are the ones that we removed.
Oh, okay.
Okay. I can get multiple input-output pairs on the same network. So this is the same network here on the right and the left. Okay. And here I think my input sites are red now and my output sites are blue. Sorry, this was an earlier incarnation. So the same bonds have been removed on both sides. Okay. But you see that if I pull over here, those 2 blue ones move together. If I pull those 2, I get a response over there. So in the same network, I could get different responses by pulling in different places. Okay? Which is also seen in Allostery. That's seen in proteins.
Now, every single one we showed, if you replace the dashed line with a solid line, you put it back
then we would totally lose it. It would be like the initial network I showed you before where nothing happens. Okay, so this is now averaged over 4,000 networks, okay, and we start, so this is the strain ratio. You start with some initial strain ratio is tiny, and now we can tune it. This is how the strain ratio gets tuned with the number of removed bonds. So I can tune it to have a negative response, or I can tune it to have a positive response, and I can change this thing by orders of magnitude. Okay, I can get up to 100 times the output strain ratio, okay, output strain compared to the input strain I put in. This is all linear response, so you have to take this with a grain of salt, okay, because this is all calculated within linear response. But I can tune, basically I can tune the ratio to be as large as I want. Okay.
Can I ask a question after playing with the model?
Yeah.
It said something being input or output, like it's obviously not symmetric.
That's right.
Why isn't it symmetric?
Why isn't it symmetric? It's not a zero frequency mode. It's actually not a single low frequency mode. Okay. Which is the other way people thought of it. Oh, it has to be a low frequency mode. It turns out that yes, it has overlap with a low frequency mode, but it's not that great. And once you get a strain ratio of about 10 or 100, it's great overlap with a low frequency mode, and that mode frequency is going to 0. But if it's a strain ratio about 1 to 1, it's not nearly, and these are tuned to be about 1 to 1, then it's not one particular mode. So it's not symmetric. If you do something at the output site, nothing happens at the input site. Yeah, it's just tuned one way, which is what you see in proteins also. Okay, so what I want to tell you is that it's incredibly easy to do this. That I can start with any input site I want, any output site, any network, okay? And I can tune this with basically 100% success until the strain ratio reaches about 100, then it gets harder. Okay, then it becomes hard to do. Okay? But if I want a strain ratio of order 1, which is what you see in proteins, that's easy. Okay? I can take a network and I can tune any response I want to it. Yeah, John.
If I have a bigger network and I push that to the right, does this curve depend upon the size of the network?
No.
to start with?
No, it does not. Okay. Although the number of removed bonds does depend, it seems to scale with the linear size of the object, not with the number of nodes. But actually the sizes that we're looking at are reasonable for proteins. And so for protein, it's saying you remove of order 5, 10 bonds, 15 bonds, it's plenty, okay? And you can see how it might happen. I mean, it's even reasonable that, it gets better and better as you tune more bonds. So you can see that you might actually get there by evolution. It's not unreasonable. Yeah.
A limiting condition would be cutting in half, which again, it's a linear, you create a number of bonds that's linear, that goes with a linear dimension. And then it's totally free, and you'll get however you move it the other side, and move in the same way. To what extent is that intuition relevant to understanding the degree of response that we're getting? So we're effectively removing a constraint on the path
that's not what's happening, right? The whole thing remains rigid, actually. There are no zero frequency. When we tune this thing, we're not introducing any zero frequency modes. So, on the other hand, there is something like the scissor motion, but if it were just a scissor sort of thing, you wouldn't be able to get a strain ratio that was larger than the linear size of the object. You have to put the pivot somewhere. Okay, and we can get things that are much, much larger than the linear size. So it's not a simple scissor thing. Okay. What? It's like it could be like a bunch of scissors that magnify on each other. Yeah. Yeah, that's right. Okay, and so now then, as you already know, because I passed this around, you can get this by laser cutting. Okay, we can make these in 2 dimensions. And this is just a movie of one. You passed it around, so you played it with yourself, but we're tuning those output sides to get closer together, and I'm pulling those 2 apart. Okay, and it really does work. Damn it. Sorry. Okay. Here's another one that was tuned to expand at that same point. Okay, so look at those 2 points. It's the same starting network, and now I've tuned them to get further apart as I pull on it. Okay. So we can actually make these macroscopic realizations. We can do it with 3D printing and make 3D ones. Unfortunately, mine broke. And they've made much better ones now that don't break by using a stronger thing at the nodes.
Where do you get the flexibility? There has to be a flexibility in the network.
Yeah.
But that 3D printer, where's the flexibility?
Although it's a plastic, I mean, that has some flexibility, just like the laser cutting thing that I passed around. So I'm not actually stretching the bonds that much. It's more rotation of the bonds. If you played with that thing. Hold on. Yeah, so we can, yeah. So, and these thick ones that we had initially, their strain response isn't that great because bond bending plays a huge role. So now they've made them so they got a different plastic at the nodes that's tougher, and they can narrow it down. If you look at the version I have, it's sort of narrowed down near the nodes, and that minimizes the bond bending corrections. But you can tune it with bond bending too. You can put in bond bending and then tune. You know, it's just a more complicated problem, but you can do that too. Okay. So that's it. That's our story. We think the universality of the jamming transition might provide some rationale for the commonality of glasses, granular matter, a whole bunch of different systems. This principle of bond level independence we're quite excited about because it's not only interesting in its own right, we'd like to understand why that is, but it also allows for this flexible tuning of mechanical properties. So the properties of disordered minima are really different from the properties of ordered minima. And we think that this might even give us some insights into Allostery. So let me just thank the people, Jason Rocks, my student, Carl Goodrich, my former student, Daniel Hexner, a great postdoc now working with Sid and me on the tuning by pruning for the Vulcan shear modulus. Scaling theory is done with Jim Sethna. Most of this was done with Sid Nagel. And the ones who made the model that I passed around, Nidhi Pashin, who's a student of Sid's, Irmgard Bishop-Berger, who was a postdoc with his, now tenure track at MIT, and Sid. Okay, and the people who provided the bread for us to jam. Okay. Thank you.
At the beginning of the talk, you mentioned about this many minima.
Yeah.
So what's the typical gap between these minima? Do they tend to become degenerate when the number increases, or are there any interesting properties?
No. So no. It just scales. It scales like e to the n, where n is. So it scales like e to the n, as I said, where n is the numbers of particles in the system. The typical size of the minimum is if you move a particle by about its diameter, you will end up in a different minimum.
Yeah, so what I'm asking is, the typical energy gap between these minima.
Oh, the energy gap.
Right.
Yeah. There's a distribution.
But isn't it like you've been saying sort of like the random energy models, you have an exponential distribution?
Yeah, you have a distribution that goes all the way down to zero. And I think it's even power law. It's a power law distribution. I think it's power law. LO energies. Yeah, the gaps. Yeah.
So in the scaling theory, why don't you use the pressure as a counterparameter?
Yeah, we could. We could use the pressure as a field. So we could use pressure and shear stress as a field. And then the compressive strain and the shear strain would be the order parameters. And if we do that, it's in a way it's nicer in that then the shear, and the second derivative is the inverse shear modulus, which actually diverges, just like more like the Ising model, more analogous to Ising. Yeah.
So if at the jamming point, if it's a really critical state, so if we can do a coarse graining, the system should look like the same.
That's right.
So do you have an idea how to do coarse graining for a disordered system?
No. That's what we're trying to figure out now. This is exactly what if we now coarse grain over a small region, I think the thing to do is just try to do real space RG, just like Kavanaugh. Yeah, and then look like the elastic constants here, and then try to then, rescaled to make it look like, you know,
How can
the
you
original system.
make sure the contact is kept?
Yeah, this is what we're trying to figure this out. Yeah, we're working with that's one of the things we're working on now. Yeah. Yeah.
So in this argument that you reviewed with Maxwell that the critical number of neighbors is twice the dimension, one of the assumptions was no friction. So what happens if you add friction?
Oh, then you have to worry about the tangential degrees, the rotational degrees of freedom too, because you've got tangential forces. So you need a rotate, and then it changes to d plus 1.
Twice d plus 1?
No, just d plus 1. So is the critical number, and then it turns out that in practice, that the number of contacts that you have right at the jamming transition can be anywhere between d plus 1 and 2d, depending on the friction coefficient